In this video, we're going to look at our truss, and we're going to look at the matrix form of the equations, because the matrix form is what we're going to need to assess these equations and solve these equations using MATLAB. What we're going to be building is the same form as we've seen before, except this time our unknown forces are going to be a vector of f's, and there's going to be some vector here, b as well. We're going to look at the next page where we tie these equations to the actual truss itself. When we look at this system of equations written out in matrix form, we can tie it back directly to the structure that we began with. For example, if we look at joint 1, and joint 1 we'll call this the top joint here, and we look at the forces that are acting on it, beam 1 and beam 2 affect that joint, and there's also a negative 15,000 Newton force acting downwards on that joint. How is that represented in our matrix? Well, if you think of matrix multiplication, this element gets multiplied by F1, anything in this column gets multiplied by F2, and so on. So it can help to actually label these columns as being coefficients of each of the forces in the truss, the beam forces in the truss, all the way up to 9. And if we take a look at these first two rows, those correspond to joint 1's force balance equations. We have sine 30 and sine 30. Those are just short forms rather than writing it out longhand. If we have negative sine 30 times F1 minus sine 30 times F2, well, that's exactly the downward forces acting on joint 1. So in fact, we have the vertical forces in this row, and we have a matching set of horizontal forces in the next row. We can continue that analysis going down. The next two rows belong to this joint here. We'll call that joint 2. If we look at all the forces involved, we'd have force 1, force 3, force 4, and force 5. Those are the beams that are touching there. And you'll see coefficients in 1, 3, 4, and 5 columns here, indicating those are the coefficients that we're looking for. If we expanded this by multiplying it by the unknown forces, we would get the equation we built for the sum of the forces equals 0 in this joint. Again, we have two equations, one vertical and one horizontal. And as you might imagine, we continue this on, we're going to have matching forces in joint 3. Then the temptation would be go to this joint down here, but remember that if a joint is pinned, then whatever unbalanced forces there are from the beams, they're automatically balanced by the pin itself. And the surprising result of that is that there's no equations of balance at the pin because there's no balance required. These forces can be anything down here, and the pin will take up the slack. So in fact, we skip over that and label, say, this joint here, joint 4. That would be the next joint represented in our equations. We can do a quick confirmation of that looking at F5, F6, F8, and F9. Scan across. F5, F6, F8, and F9 are represented in the matrix here. Last but not least, we have the roller. We've discussed that previously. The only forces that have to be balanced on the roller are the horizontal. The roller itself will apply any necessary vertical forces to balance things out. And so that's how we build the entire A matrix in this system. What about the B vector? What's not represented so far? Well, if we take a look at joint 1 as an example, there's a 15,000 Newton force that isn't captured by the A times F here. So how do we bring that 15,000 newtons in? Well, just remembering that joint 1 vertical would have negative sine 30 times F1 minus sine 30 F2, and then it would be minus 15,000 equals 0. What we're going to have to do, though, to make it match the form here, the left-hand side, we have these two ingredients already. Those are sine 30 and sine 30s. However, the 15,000 doesn't fit on the left-hand side. It has to get moved to the right-hand side. And so we just move it over there and remember to change the negative into a positive. So that's what we get on this side here. However, the temptation is to put the other two 5,000s first thing after that, but just remember where they come from. This second equation represents the horizontal balance in joint 1. Well, there is no external force, there's no 15,000 or 5,000 applied horizontally on that, and so we simply have a 0. These forces here have to add up to 0 in the horizontal direction. This 5,000 comes in when it's applied to joint 2 in the vertical direction, so it corresponds to the third row in this matrix, and that means it's going to get a 5,000 value in the third row of the B vector. The fourth row was horizontal forces in joint 2. If we look at all the forces applied here, there's no external horizontal force, so we have a 0. And only when we get to the third joint, joint 3, the vertical equation, we add up all those forces, and we should get that minus 5,000 equals 0. Or we do the same trick again, we bring that 5,000 to the right-hand side of the equals in our equation, and it turns positive. And after that, we end up with zeros all the way through the rest, because there's no external forces on the horizontal joint 3, either the directions on joint 4 or on the roller. Having done that, we can see some structure in the matrix that we built. A is all about the internal geometry. The elements in the A matrix are all sines and cosines having to do with the projection of a beam direction onto the horizontal or vertical axes, and which direction is it going in, negative or positive. The B vector is where we capture all the external forces. Anything that's not a balance in the internal beam structures, like these 5,000s and 15,000s, those end up in the B vector. And how do we determine the row that a particular B value appears in? We just look at the geometry, and specifically we look at the equation represented in A. So if we go back again, we look at a row in A, and we say, well, which balance equation is that? That's the vertical balance for joint 1. Oh, there's a vertical external force on joint 1, so that's where we'd get a value for our B vector. The second row of A is all about horizontal forces on joint 1. There's no external horizontal force, so we get a 0 on that. And let's be more specific here, represented in each row of A. Each row of A represents one equation, and we just need to know where that equation comes from and whether it includes an external force or not. Let's take a look at this in MATLAB. If you download the file W23, and we're going to put the B values in, and we're going to check the shape of that as we look at it. So I'm going to focus on A first. There's this dot, dot, dot that just lets us start the matrix a little bit lower and made it easier to line things up. You'll see all these S30s, C30s. Those are not built into MATLAB, so the opening lines are up here, and those essentially define what sine of 30 is. Notice that you can use the sign D, which does sines of degrees, or you could use the regular cosine sign, which use radians, and then convert the degrees to radians through the standard, divide by 180, multiply by pi. We build our A matrix here, and then we build our B vector in that same order. Notice the semicolon so that we get entries on new rows. And then last but not least, we have the solving procedure. I would like to solve for the unknown forces in the beams, and that's the solution to the A times F equals B, and we know how to solve that using the syntax A/B. That'll trigger a Gaussian elimination and give us the unknown forces. So let's do that to actually solve for the forces. All we have to do is run. There we go. With that, we've obtained a set of forces, and our challenge really now is to interpret those. So keeping in mind that this force vector is exactly what we wanted in some sense, we now just have to figure out what it means for us. Here we've pasted over the actual values. They're a little small, so enlarge them on your own screen if that helps. But the key thing is each of these maps to a force, and this force numbering matches the original description that we had a few slides back that we used to build the equations. These forces, 1 through 9, are represented in a certain order. This beam, this beam, this beam, the 4 across here, and then 8 and 9 is the 2 bottom beams. With those in mind, and notice this times 10 to the 4, we're basically talking times 10,000. So we actually have a force here of 15 kilonewtons in this beam. It's negative, so it's in compression. And if we want to add that as a force vector, that means it's pushing out. To resist that compressive force, it's pushing out on the joints on either end. And the same is true for beam 2. And we can see that makes sense. We're pushing down on the vertex at the top, the joint at the top, and we get a resistive force, totally matched, totally symmetric because of the way the forces are being applied, totally symmetric to resist that force. We can then go on and see what F3 is, and it is in tension, so it is pulling inwards at a force of about 5.7 kilonewtons. So a lower load here, but it's a tension force which is avoiding this joint popping out. Moving down the list, we have compression again at about 14.4, let's just call it 14 kilonewtons for now, rough scale. And then, interestingly, we have 2 zeros, and then another compressive force negative of 14 kilonewtons. And last but not least, our 2 forces at the bottom of about 7.2 kilonewtons. These are both positive, and so they are tension and pulling away from the joints. And with all of that, we can see that there's a reasonable distribution of forces here. We're pushing down on the top, that's resisted by compressive forces. This compressive force here is pushing outwards. This one's pushing inwards a little bit, but this force here is going to overwhelm it. To balance that, we're going to need some tension in this cross member here. This is pretty standard in truss designs, that the outer rim is in compression and the horizontal members end up in tension. And we see the same thing replicated down here at the bottom row. We have a force that's pushing outwards, but to balance that, we have to have an inwards tension stopping this truss from expanding outwards. And so this worked. We do have to do some interpretation. We have to remember how we labeled all our forces. There's multiple ways we could label these beams that would have changed how this output looked. But the forces that we end up with, the balance that we have to maintain, given the geometry and the external forces, we would have to end up with this unique solution for a determinate truss of 15 kilonewtons here in compression, 5.7 in tension, and so on throughout the rest of the structure. In summary, what we went through there was deriving a set of equations that determine the balance of forces. Let's make sure that's implied in there, that we have the balance of the forces at each joint, horizontal and vertical. And we take away some equations for the supports. That's because some of them are automatically balanced by the pin, both horizontal and vertical, and the roller will automatically balance any vertical forces. We then convert those equations into a matrix form so MATLAB can interpret it. Then we use MATLAB to actually do the solving part, and that is our masterful F equals A/B, which just went ahead and solved that 9 by 9 system of equations for us. And then the most interesting part is spending a bit of time interpreting the results and making sure that we understand what the meaning of the values we get back is in the context of the original truss.